Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be putting all the addition reactions in one spot and helping you decipher which one will be best when we synthesize. I'll link the previous videos down below and make sure you hit the bell icon to get notified when new videos drop. We've also started doing a podcast format for those who'd like to reinforce the concepts on the go, and I'll link those down below as well. So we're going to start off by using methyl cyclobutene as a starting material. This will help depict any stereochemistry when applicable with certain reactions. Now, if we start in wanting to produce an alcohol on the more substitute carbon, there are two ways that we can do this. Now, if we move to the right, into this study aid, we see that there are two ways that we can produce an alcohol on the more substituted carbon. The first way is the acid-catalyzed hydration, which is circled on top, as well as the oxymercuration demercuration, which is also circled right here. Now, either two of those will give an alcohol on the more substitute carbon, but there is one slight difference. So if we go through the acid-catalyzed hydration, we have water and an acid catalyst. The first step is the protonation of the double bond by the acid and then the formation of the carbocation. Now, because we form a carbocation, rearrangement can occur. The second step is water attacking the carbocation, and then the last step is the deprotonation of the water to give an alcohol on the more substituted carbon. Now, if we look at the oxymercuration demercuration on the first step, the double bond attacks the positively charged mercury and forms the mercurinium ion. Now, due to the formation of the mercurinium ion, no carbocation is formed and thus no rearrangement can occur. The second step is when the water opens up the mercurinium ion and is followed up by the deprotonation, the third step. The final step is the sodium borohydride, which is NaBH4, which is a reducing agent, removes the mercury and then replaces it with a hydrogen atom. Now, both of these are a correct way to create an alcohol on the more substitute carbon. The difference is that one forms a carbocation and one doesn't. So the question is, which one would you use over the other? If you're worried about rearrangement, use oxymercuration demercuration. If you're not worried about rearrangement, you can also use the acid-catalyzed hydration. Now, if we look at this, these are the reagents that we'll use. On the top, we have the acid-catalyzed hydration. Note with this that we do have rearrangement that will occur. And on the bottom, we have oxymercuration demercuration reagents. Again, note with this that we have no rearrangement with this type of reaction. Now, if we look at the next example, we are trying to have an alcohol on the least substituted carbon, meaning it is the anti-markovnikov product. We also see that we've introduced some stereochemistry, and in this case, it is the Syn Addition. Now, if we move to the right, we can see that the Hydroboration of Alkenes, which is circled right here, will produce an alcohol on the least substituted carbon and also adds a Syn Addition. And so if we move it to the right, look at the mechanism, we see that the first step, the double bond attacks the boron, and then the hydride shift occurs at the same time. Now, take note that the boron bonds with a carbon that is least substituted with the alkyl groups, and that's because it is bigger to hydrogen relatively. And if we remember the concept of steric hindrance, it would naturally bond towards something with less steric hindrance. We also observe a Syn addition, and that's because the first step we mentioned that the double bond attacks the boron and the hydride shift happens at the same time. Now, because of that, the addition of the borane and the hydrogen must be on the same side of the plane. The last step is the oxidizing of the boron with peroxide to replace the boron with a hydroxy group. Now, we notice here that there's no rearrangement that occurs, and that we have a Syn addition of the alcohol. Now, the next reaction that we want to look at is adding a halogen to the more substituted carbon, which is the top reaction, and then we also want to add a halogen to the least substituted, which is the bottom reaction. Now, if we scroll to the right, we can see right here that The way to add a halogen on the more substitute carbon would be the hydrohalogenation of alkenes, which is this right here. And if we look further to the right, we can see the mechanism for the hydrohalogenation. The first step is the double bond gets protonated, which in then turns produces a carbocation. And as we remember before, we want to have the carbocation on the more substituted carbon due to the stability. Another note is because we have the carbocation formation, rearrangement can occur. Now, because of this, we know that proton is added to the carbon with more hydrogen substituents, which makes it the Markovnikov product. Last step is that the halide attacks the carbocation to form the product. Now, if we move back to this study aid, we can see that the way to add the halogen, specifically in this case the bromine, to the least substituted carbon would be through hydrobromination with peroxide, which is this right here. And so, if we look at this reaction right here, these are the reagents that we'll use. This right here is the hydrohalogenation of alkenes. And then this is the hydrobromination with peroxide to have the bromine on the least substituted carbon. The next type of reaction that we'll look at is moving the bromine over one carbon and then changing it to an alcohol. Now, the first thing we should do is create a double bond that we can add a reaction to. When we form a double bond, we have to be aware of the products formed after the elimination reaction. A more substituted alkene, which is the Zaitsev product, or the least substituted alkene, which is the Hofmann product. Now, if we use a bulky base, such as tert butoxide, we form the Hofmann product. If we use a non-bulky base, such as ethyl oxide, which is this right here, we form the Zaitsev product. Now, if we look at the mechanism down below, the beta hydrogens that are possibly being abstracted are depicted. And this right here is just a depiction of the mechanism of the beta hydrogens being abstracted to form the products. Now, the top shows that the tert butoxide as a bulky base, abstracting a beta hydrogen to form the least substituted alkene. And yeah, if you follow the mechanistic arrows, that's how that will go. And then the bottom shows ethoxide as a non-bulky base to form the more substituted alkene. Again, the red mechanistic arrows show how that will work. So we know that we have to use a bulky base to form the least substituted carbon, or least substituted alkene. And then we want to finish the reaction off with the hydroboration of alkenes, and that will produce a alcohol on the least substituted carbon. The last type of reaction that we'll look at today is the addition of a double bond. Now, if we notice, there's no leaving group to allow the elimination reaction. If we introduce a functional group, or we must introduce a functional group to allow the elimination to occur. Now, we can do that through radical bromination, which involves N-bromosuccinimide, which is also notated as NBS, and light, also noted as HV. Now, because a radical is formed, we form the more stable radical, and it would be a tertiary in this case, and then add the bromine to the tertiary radical. Now that we have a functional group, we can use it to initiate the elimination reaction. The last step is picking the correct base to form the least substituted alkene. So again, this is the slide of showing a bulky base as well as a non-bulky base. The top portion shows the bulky base such as tert butoxide to abstract this beta hydrogen to form the least substituted alkene. The bottom portion shows the non-bulky base like ethyl oxide to abstract the beta hydrogen to form the more substituted alkene. Alright, so that concludes this video. Shown below are these reaction study aids with all the reactions that we've all went over, as well as some others just for completion's sakes. And also is the alkene reaction agents into a tree form. The first part is the alkene reaction with all the reagents as well as side notes of stereochemistry. Second part is just the alkene reactions with just the reagents. And then the last part is just a blank reaction for you to practice on. So hit that like button, the subscribe button, support the channel and share it with your friends who need help with organic chemistry. In the next reaction, or in the next video, we'll be going over alkyne reactions. We'll put more videos up, and let me know down below what you'd like to see next. Social media links are down below, and as always, remember, you gotta go.